And so Dr. Williams got his PhD in 2005 from Syracuse University and came to ENC the next year. So 2006 she started at ENC, and he held a part-time position before this at Savannah. Dr. Cornley didn't tell me where, university?
Armstrong.
And does research here at ENC with the students. He's published a number of articles in peer-reviewed journals, and a lot of them with students. He has 3 publications with students, something like that, which is very good. That's one of the things that should be unique about ENC is we do research with the professor here. He also won the Teaching Excellence Award in 2011 for teaching organic chemistry. He works on new phosphorus compounds. I'm not sure what kind of old phosphorus. New phosphorus compounds. He's working with undergraduates. They've done posters and talks at both the regional and national level. So it's a great pleasure to welcome you, Joe. I'm supposed to say to the John Free Lecture. Money, but anyway. And he's going to talk about lighting candles.
Yeah.
Stealing your thunder, lighting candles in the dark.
Yes.
All right, thank you.
Thank you. All right. So. So as the my theme suggests, you guys have no idea what I'm going to be talking about. I can talk about anything. What this
Sounds really romantic.
All right. All right. Well, you could either call it this, or we could also, have themed the talk as making chicken biryani. Either of these will work. See? So. We'll try to dive
Inside joke or something.
I like that.
All right, so the talk is going to be about the research that students have been doing under my supervision here. Right? Okay, so since we are going to be talking about the students' work, I'll introduce you to some of the students that did this work with me. Right, you come into ENC and promise you all the good stuff. The best students, the best faculty, the best facilities, and so on, right? These are the students that work with me. Some of you may recognize some of these guys. These are all the guys who work with me. And then, ready to leave and go, thankfully, somebody like this shows All right, so we have a few more students. Mike, Sejun, see. All right. So, really brief intro to my chemistry career. So, did my master's in India, in Chennai, Madras, and I worked with tris chemical silicates and attempted to do studies extracting metal ions from solution. For the physics and engineering people, thought I'll put up some structures so you're forced to look at some organic. Yeah, so so these are silicates, and these are called hypervalent silicates, forming more than the usual 4 bonds. And basically, the idea was to replace these amines with metals. So So metals are present in really small concentrations, and throw this in, and hopefully in extraction we can link the metals up with the silicates and extract the metal ions out. Right? That was my master's work, and from nice warm 90-degree weather, right, I landed up in Syracuse and worked on making ruthenium cat olefins. This is what you do after 5 or 6 years of PhD work. Right? You're able to put that in one sentence that tells you that you have a PhD. Right, what did I do? But the idea was to take an olefin, right, basically an alkene type molecule, and put metal centers at the ends and study electron delocalization or localization between the metals. So one of the projects of the group was to maybe take these and look at how the electron flows from one end to the other, and perhaps use them as molecular wires and so on. Right? Okay, so, all right. What did I work with? I worked with this ruthenium compound as the capping agent. So we take the ruthenium complex, and then where you have this double bond here, you basically link the olefin together. Right? We'll come back to this in a minute. All right. So the main part. Okay, I pressed it. Oh, that's good. All right. Yes. What is this? Right. All right. What do these look like? King and queen. Nice. King and queen. Well, for the non-organic chemistry people here, there you go. King and queen atoms of organic chemistry are. Anybody? Carbon and hydrogen. Right? So, right, in general, we have carbon with 8 electrons around it to make it nice and stable. Right, that's the standard, right? Octet rule. Nice. Very nice. Sometimes, if the carbon has only 6, then we know it's not good. Right? That kind of a carbon is called a carbene. And carbenes is what I worked with in my graduate studies. This carbon right here, that carbon is actually a 6 electron carbon. We don't show the charge, and we don't show the missing atom. That's only 6 electrons right there. Now, traditionally, right until the 1980s, 1970s, you basically would not find any literature about carbenes because they're supposed to be unstable. How can you isolate a carbon with only 6 electrons around it and actually work with it? Right? But in the early 1980s, a couple of people reported the preparation and isolation of these 6 electron carbons, and they were actually able to isolate the compound, a pure organic compound, that one of the carbons had only 6 electrons. It wasn't a salt, it wasn't protonated, it was just, it was one of the first carbenes to be actually isolated. And so work done in that area was to take the carbenes and then use them as ligands, bind them to metals. Right? In fact, one of the guy who won the Nobel Prize in chemistry in maybe four years back, Robert Grubbs, he actually worked with this pretty much this complex. His work was on this, using carbenes to bind with ruthenium metals and do other studies. Right? Okay, so that's a carbene, and this is what I worked with. So when I came to ENC, my plan was to, so far, in the literature, so that was 2005, there were reports only on this type of carbene, where we have the carbon attached to 2 nitrogen atoms. basically to stabilize the electron deficient center. Right? But no work was published where we had phosphorus atoms replacing the nitrogen atoms. And the only work that was in the literature was theoretical work that basically said, well, if phosphorus replaces nitrogen, there's an equal or even higher probability of phosphorus stabilizing the carbene atom, which is great because then you're going to have a more stable catalyst in catalytic cycles. So that's what I thought I would do, right? If Robert Grubbs was able to get a Nobel Prize based on this book. No? Okay. So that was what we initially started off with. Right? Okay. So catalyst. What's a catalyst? Right? If you are in this day at 7:44 in the morning, and you want to go to this at 7:45. Catalyst, right? All right. That's what I want. Okay. So synthesis 1. That's right. This is what organic chemists do. They design synthesis. That works or not, that's something else, right? Designing synthesis. Okay. So, right. Starting off from phenylphosphine, add an alkene, amine, use a radical initiator. The plan was, right? You make this, you just basically do an addition reaction, do a simple formulation, and then use a base and close the cycle, the ring. Okay. The results of this, right? In my first year working with students, basically nothing much to talk about. We got a big mess right here. I should have known better, right? These are radicals. Radicals are radicals. They do crazy things. They do the unexpected. So what I got out of that was, well, it's time to move on to another synthesis. And so we went ahead and designed synthesis 2. Right? Synthesis 2 was designed to not have any radical initiators present. So in this synthesis, started off with a readily available dibromide. Right? It's not very clear. Right? You throw in a triethyl phosphite, right? Do a simple substitution at this carbon. Then you substitute at this carbon with this azide, do a reduction, you form this acyclic aminophosphine. That was the plan. Then the second stage, take the phosphine and you cyclize it initially, right? And do a few reactions to form the carbon. Okay. So, right? See what happened?
Go back to the last one. So you're just replacing one of, you still have nitrogen in the one down at the final reaction. You're not replacing both, it's just one with a.
Hydrogens?
You go back 2 or 3 slides and compare what you were doing.
Yeah.
Further back. Right there. 1, 4, right there.
Right, yeah, so yes, so these are both phosphorus atoms, right? So yeah, I worked with both nitrogens, and in these syntheses, just replacing one of the nitrogen with phosphorus. It's supposed to be the easier one to do.
So do that one first.
All right, so organic chemistry for the people who refuse to take organic chemistry. See, this is what happens, right? You take this aminophosphine, you throw in this reagent, nitrogen attacks the carbon, kicks out an MEO molecule, then the phosphorus comes along. That is its job. Get out, right? And we have the cyclic compound, which then loses another molecule of MEOH and forms the precursor to the carbene. Right? Okay. So what came out of this? There we go. So we were able to go from the dibromide all the way to the aminophosphine. Right? and Joe deserved, and Sean worked on this. Tyler also worked on. He worked on the two carbon bromide. No, I'm sorry, the 4 carbon dibromide. This is the 3 carbon, right? Okay, so we made this, and then Sean has been currently working on trying to cyclize this. Right? Now, we know that, right, we know we have this for sure, but we're not sure what's going on here. On cyclization, we don't know what the actual product is as yet. But we know that's something new that is not this aminophosphine. So, we're trying to presently, right, figure out what we have there. But in the meantime, as we're doing that, Sean has also he's done a few experiments trying to see if this can actually work as a ligand right at this stage. Because from here on, these are all new compounds. Every reaction is generating a new type and series of compounds that haven't been published in literature. So, but the easiest thing to do would be, well, let's see if this also works as a ligand, because phosphorus and nitrogen are really good, ligand bases. So, well, and initial data suggests that this is in fact, whatever this is in fact forming ligand bonds to the metal. Used down with nickel, sulfur, and it looks like we're going new complexes, right? So that's where that is now, right? So there's room in this project to take this, figure out what we have here, and then continue with the synthesis, the proposed synthesis, and go all the way to the carbene.
Where's the extra carbon coming from?
Which carbene?
Between the phosphorus and nitrogen?
Where is the extra carbon coming from? Right, oh yes, so that's why we use the trimethyl octoformate. I want to show you that. Yeah.
Oh, okay.
Yes, that's the carbon. Right. Yes. Yeah. All right. So that is synthesis 2, which is he's working on now. But obviously, these projects have not been. It's not at a time increasing time and scale. These are being done all over these past few years. Some students come work on this, leave it. Some of the students come to work on something else, leave that, and then some students come later, continue from where other students worked on. Right. So while this was going, I had also have students working on another proposed synthesis of these PN heterocyclocarbenes. Now, right, in this case, we no longer are starting from plain dibromides. Now, now I have this acyl here. The reason is I want to distinguish between the reactivities of these two carbons. Right? Because having just 2 CH2 carbons here doesn't really help us in differentiating reactivity. So you make one an acyl, a Cl group, and one a CH2, then we can we can tune the reactivity. Right? So the proposed synthesis. There we go. Right? You take this readily available fluoroacetyl chloride, you throw in an amine. Right? Here's the other difference. Right here, at the very first step, we have flexibility. We can change. This R group simply means you can have any carbon skeleton to begin with. So right here, at this very first stage of the synthesis, we can get, we're setting up ourselves to get a bunch of these products. See? So that's right there. So now this reaction is a standard reaction. In fact, some of my organic chem students currently, they're doing a project, just using this reaction, something, using this reaction. Right? So this is standard. So this should be fine, no problems about that. Now, from here on, these are all new ones, right? So, but the idea is, instead of using an amine, we use a phosphine. Now, if this was an amine, it would react here first. That's what we expect to do. Then the phosphine should now react at this carbon, right? And you do reduction, reduce the CO bond to the CH2, cyclize, and form the carbene, right? So, in hindsight, there's nothing really here to be worried about. These, even though these reactions haven't been done on the specific substrates or type of substrate, the reagents and what they do in general, should mean that these should work out. All right, what happened? Okay, so, right? Well, so when we took the amine, all right, this is what happened. Right? That's why it's modified. We took this, right? We did the chlorides. In fact, we did a bunch of these chlorides and bromides. Right? We took the amine, we took a bunch of the amines. This worked just fine. Nice. Then we added phosphine. So we worked with phenylphosphine. And we tried adding it to this first product. But reaction would simply not go. It would, the phosphine would not react at the CH2Cl. Now that's in contrast to the amines. See, if you use an amine here as well, in the second step as well, it will react. That's that's reported in the literature. Amines will react both at this carbon and as well as this carbon. See? But for some reason, our phosphine here would not mess around with this carbon. All we would get was this product. There was nothing else forming. No matter, we changed the base, right? We changed the solvent, we changed the nucleophilicity of the phosphine. Nothing going. So, what did we say? Okay, instead of adding the amine first, let's add the phosphine first, right? Because this is the more reactive carbon. Right? This is more reactive than the CH2 carbon. So, for some reason, the phosphine is not reacting at this carbon, which is not as reactive, but still reacts. Well, let's add the phosphine first, and I'll sort of guarantee that it reacts with this carbon. So we did it. Yes, nice, it worked. The phosphine, in fact, did react at the CO carbon. It worked. Right? Now all we had to do was throw the amine in, get it to react here, which it's known to do, right? And then reduce it, and we get back, to our stage in the synthesis. See, ultimately, what is it? We want to get to this aminophosphine. So whether we have pH here or NH here, it's going to work the same because it's going to reduce it and get the same skeleton, right? So nice. We made a bunch of these. Then all right here, right? All these are new compounds. This PCO bond is not really reported in the literature. There's hardly any data in the literature for the PCO bond, right? We know a whole lot about the NCO bond. That's the traditional amide, right? But the PCO is not found. Okay, so that's great. We took the amine, and this is what we expected. Well, you know what that means? Expected. What we got was the phosphorus. What happened here? The amine went ahead and replaced the phosphorus. No matter what we did, this would not go and attack here. It just kept replacing the phosphorus here, which is, just not how amines work with these type of reagents. Because amines will first attack here, then they attack here. No big deal. But in our case, this would not go here. It simply kept going to the CO, kicking out the phosphorus. Okay, so, well, why is it doing this? Okay. So alright, so the next step was, okay, for some reason it keeps going here. Now let's try to change, make this even more reactive. Give the amine reason to react here, right? So, right, Cl in the process leave, that's a good leaving group. Let's make it even a better leaving group. So, we took the Cl and we made that into the bromides, right? We made it into the bromide. So we made this bromide, we did a few variations. All right, what happens? Right, with the chlorides, we know the phosphine attacks here and takes the chloride out, right? So we said, okay, let's do with the bromides. And once we change chlorides for bromides, we got something again. So like, what? This is not supposed to happen, right? I mean, these are simple reactions in organic chemistry, right? These are standard reactions that should follow the rules, right? And we phosphorus, right? What's different between these? This is Cl, this is Br, right? Same group, and Cl is a good leaving group, Br is even a better leaving group. So you would think I would form even more of a similar product here. No. We get this dibromophosphorin compound. How is this even forming from this? Right? Right, it took a while for us. In that summer, I was working with 4 students and a couple other students. Right? It took a while for us to figure out that we had this because, for one, we didn't expect at all. And the structure is a little different from the usual, structures that we're used to seeing. So finally somehow, right, after many experiments and searching, we figured out that that's what we had. This is dibromophosphorin compound. Okay, so, well, yes, right. Yes, so what we did? Well, let's see if this is something general. Is this just an issue with the dibromo we have, or is this how phenylphosphine reacts with acyl bromides? And here we go, right? So we did a bunch of these acyl halides, and I'm showing you a few, right? And right, so there we go. So the phosphine does seem to form the same compound with a COBr functionality, right? Took that, then we stuck the Br here as well, but kept the Br here. Same compound, right? Then let's switch. Let's take the Br out from here. Let's put Cl. Well, there we go. Now we get back what we think we should get, right? Now the phosphine is going here and taking the Cl out. But it doesn't want to do it when the Br is there, which is right, unusual. I mean, the organic chem students in lab, what they're done with Cl and Br with the amines, and you get the same product. Not the case here. And I don't know why that's the case. It's not supposed to happen, but it is happening. Right? So then we took just the Cl here, right? And what the bromide, well, it does what it's supposed to do. pH attacks the CO, kicks the Cl out. So, the take home on this is, when we have the Br bond attached to the Cl, phosphine doesn't want to go attack the carbonyl, it is just picking out the Br. When we have the Cl, it does what it's supposed to do. It attacks the Cl group and kicks the Cl out. Right? So basically, we have tried various that I could think of to get this reaction going. Right? We change the solvent, the base, we change the reactant, right? Make it into better leaving groups, give it some reason to react, and it doesn't want to do what we expect it to do. Right? The only reason I can think of for phosphine not picking up, not attacking the CO is maybe the size of Br. Just maybe phosphorus is a little big, too big to go approach the CO and take the Br out. And so it rather goes unusual, right? Atypical. Attacks the Br and picks up, 2 of the bromides to form the phosphine dibromide. So that's a new, that's not really found in the literature. This debromination of acyl halides using using nucleophiles. Nucleophiles don't really act, like this. They attack carbonyls. They don't attack the atoms attached to the carbonyl. But this does, right? So a little increased understanding of the PCO bond, right? Okay. So what do we do? Well, this is what we have. Let's try to do some more work with this. So we went ahead and did a few studies, some of which I'm talking about here. Right? So if you take a 1:1 ratio of the acyl halide, the chloride with the phosphine, right? You form what we term the mono, where the phosphor attacks the CO, kicks the CO out. Now, what happens if you take a 2:1 ratio? Right? Well, now what happens? Now we get what we call the bis compound. So basically, the pH bond, right, it's pretty acidic, and so now we have 2 of the phosphorus, 2 of the chlorides bonding to the phosphorus. So by changing the ratio, we can make the mono and this version of this compound again, right? Phosphorus is not going to CH2 carbon and attacking the carbon there, it prefers attacking the CO bond. Right? Then you can also interconvert the mono and the bis by, right, like an equilibrium here. Right? If you take the mono, you isolate the mono and then you throw in some of the acyl halide, you get the bis. Or you isolate the bis, you throw in some of phenylphosphine, you get back the mono. So you can actually track the formation of, you can go from here all the way to the bis by using spectroscopy, changing molar ratios. So we did some studies, we did some stability studies with these, we tried some reactions just to investigate these compounds if they could be useful in anything, just basic science. Alright? Then, okay, guess we have one more shot at this. And that was, so we took the bis, said, okay, well, let's take the bis compound and try, reacting that with maybe this may do something. Well, it did, but it didn't do what we wanted, right? What has it done? Looks like the NH went ahead, attacked the CO, and picked the phosphorus up. So, the CH2 is being really stubborn and not doing what it's supposed to do, right? So, what else did we do? Yes, just one reaction that I'm throwing in, right? Right, so we took the bis, for example, right, and you try oxidation. Now, the reason to try this oxidation is that the phosphorus oxides are known to be, good initiators in radical reactions. And so, okay, well, let's see if we can, oxidize the phosphorus atom, make it into a T double bond O structure. No, that's not what happened. Instead, we cleaved the PCO bond and got back a carboxylic acid. Okay? It's a new reaction. I don't think that's one, we want to use this reaction to make carboxylic acids. It's really much easier. All right. So that's that part of the phosphorus project. Yeah? Yes. That's where the phosphorus, we did a lot more work. Unfortunately, I'm not going to be talking about that. And the students who worked on that, Talia, Mike over here worked on it, and had a bunch of Ross, and Allie, Moles, David, Holly, Rebecca, so I had a bunch of students working on this over the space of 2 years, 2-3 years, in the summers basically, when they did that work. Right, so there's definitely room to push this to see if we can make these carbenes from either of these syntheses, right? Okay, all right. Any questions? Switch gears. All right, switching gears. All right, so switching gears. Here we go. Nice. What is this compound? Anybody know what this compound could be?
Caffeine.
Caffeine. That is good old caffeine. Yeah? Take a good hard look at this. Chemists. This is the stuff you're drinking. Caffeine. All right. So, this project came about through the senior project time. So I had one of my students, Mikhail Bowie, and he was talking with me, and we were discussing what shall we do for the senior project research. And so he said he wanted to work with caffeine, do something with caffeine. Okay, well, let's see what reactions are out there in the literature with caffeine. Let's try something new. All right. And so we decided that we'd try a Diels-Alder reaction. A Diels-Alder reaction is a standard organic chem reaction. And we looked at the structure of caffeine and said, okay, it has some parts that resemble what we want for a Diels-Alder reaction. All right. And so if the Diels-Alder reaction does take place, then this is the product that we would expect to recover. Right? Okay, so you went ahead to the lab and you tried the regular Diels-Alder reactions, followed the literature, and nothing happened. Right? So then, when we talked about it, I said, okay, let's give one more try. Let's try doing the reaction, but with no solvent. Now, usually, reactions we usually add solvent because we want the reaction to go. We need a common medium, and so it's usually done with solvent. But both these are solids, and so we said, let's just heat it up neat. It's called a neat reaction. No solvent, just go directly heat. So he went ahead and heated, and from that stemmed the following slides. Right? Yes. And to our amazement, what is this? So we take these nice white solids, right? Caffeine is nice and white, and melling anhydride is nice and white. And this, all we do is simply put in a test tube and stick it in the Bunsen burner or a sandbar, and we get a nice green colored looking species. Nice. Okay. Then comes the fun part, right? We take spectra. We take NMR spectra. They're basically spectra that help us decide what the structure of the molecule is. So we take these spectra, and the spectra looks almost, I put the almost in, it looks almost identical to reactants. So pretty much, right? Pretty much, if you look at the spectra, you find, okay, the same peaks of the reactant are present in the spectrum. Now, how can that be? Because we do see a physical change in color, right? But structurally wise, it seems like it's pretty much the same. Okay, we take IR spectra, right, another tool to analyze structure. That also looks pretty much the same, peak for peak. Okay, right, so what do we do? How do we now account for this? So, what we did, well, we ran a bunch of other compounds and see if other compounds would also give us the green color, and in fact they do. You know, all these, right, these diacids, this anhydride, these do give the green, colored compound just by merely heating the two together. Take caffeine, you take this, that's heated, that's it. You get this greenish color. But then there are compounds that don't. Right? I had Ryan, who is not here. He graduated a year or two back, and he ran, 15, 20 compounds. Basically, we went to the stock room. Okay, let's try this. That's literally what we did. Like, what is going on, with this green thing? And so we found out a few, in fact, do give the same color, and most of the others do not give any physical change in color. Okay, all right. So, what do we do next? All right, yeah, here's the IR spectrum. It's not really very. It looks better on my computer. All right. Yeah, sorry about this. This is not the best, but there is really no new peak form. Pretty much you have peak for peak overlapping, right? So in one case I have the green, which is pure caffeine. In the other case I have melling anhydride, and I have the green product. So pretty much we have peak for peak. Either the green product matches peaks for melling anhydride, or the remaining peaks match for caffeine. So there's really no new outstanding peak in the spectrum, right? Then, okay, we took NMR spectrum, all right. So here's a nice, yes, you can see this, right? So here we have plotted delta ppm, right? This is in NMR spectrum versus mole fraction. Okay, what is it we did? Right? So we made a bunch of solutions of caffeine with melling anhydride, heated it up, right? And then took the solid, the liquid, and then dissolved it in our solvent to run spectrum. Right? And so we did that for a bunch of molar ratios of caffeine and melling anhydride, right? And then took the spectrum. Now, right? I mentioned that before, right? The spectrum looks almost identical. So right here for caffeine, pure caffeine, right? Pure caffeine comes, so there are different peaks in the spectrum, right? So we focused on one of the peaks. Pure caffeine comes around 7.50, maybe 503 or 504, right? ppm, right? That's pure caffeine. Now you add melling anhydride and you're focusing on the same peak. As the mole fraction of melling anhydride increases, the peak that is supposed to be at 7.50 actually starts to shift. It goes all the way from 7.50 to 7.57. The same peak that belongs to caffeine actually shifts as we increase, the concentration the molar ratio of Melling Anhydride. Right? Now, what does that tell us? Right? So you look at the literature, based on similar studies. This kind of a study is done to show association of molecules that have properties of electron donors and acceptors, and that will actually form weak intermolecular forces of attraction in solution as we change the ratios of these compounds. And this is pretty much what you see in the literature, where there's a change in the spectra of the compound of, let's say if you pick a certain peak, it changes not by a whole lot. See, it's very small. It's still 7.5, but it's 7.50 to 7.57. That's the really small changes that you would expect to see if you have weak forces of attraction between molecules and solution. Right? Okay, so then we ran a method called Job's method. Right? And if you have any questions on that, you can ask Dr. Reed. She'll be more than happy to answer that. So all questions on that to Dr. Reed. Okay, so you ran a Job's method, and the Job's method looked somewhat strange to me. Now I'm an organic chemist, right? I don't know a whole lot about Job's method. So you read up on what's out there in Job's method. Usually, to my knowledge, right, you see one peak in a Job's method. What is a Job's method? It's similar to this. We take different mole fractions or molar ratios of two compounds, and you keep the total molar ratio constant. Right? So totally, say you want a 1 mole. So you take, say, 0.5, 0.5, 0.4, 0.6, and so on. Right? Which is what we did here. We kept the molar ratio, total molar ratio constant, right? So we pretty much ran the NMR spectra, and for the same solutions we ran UV spectra, and we recorded the absorbance of these solutions, right? So you plot the absorbance versus the mole fraction of caffeine in this case, and we get roughly what looks like two peaks, two bumps in the Job's method. Now usually, right, we see one triangular peak that suggests the formation of one complex in solution. This seems to suggest two complexes. I haven't seen any spectra like this. I don't know if Reed, all right? Dr. Reed also nodding. So yeah, I am not really sure. It seems like we should have two complexes forming. I don't know. That's what the Job's method seems to suggest, right? It sort of falls in line with this because this is suggesting different complexes, because that would then lead to different peaks in the NMR spectrum. So right now it's sort of a mystery that we can absolutely investigate further. This is right solution phase. Right? This is solution phase, both NMR spectrum as well as UV vis. Now what I'm going to talk about next, for the next few minutes, is going to be the solid phase of this complex or this species. Right? Okay. How are we doing on time? I have no watch on me. I'm just going. Did you go countdown?
Approximately 5 minutes.
When did we start?
If you want to have questions and answers, but you have
5 minutes. All right. Wow. I thought I'd be done in 15 minutes. All right.
Don't worry.
Okay.
You don't have time.
Huh? All right. So, right. So this is exciting stuff right here. Yeah. All right. So what was the idea? Well, so you look at these structures of caffeine and melling anhydride. The idea was, okay, it looks like these may be electron donors and electron acceptors. Melling anhydride is a nice dope, it's an acceptor, the standard electron acceptor. And caffeine is able, it has this pi bond, maybe it's able to donate electrons. So the idea was, well, perhaps melling anhydride is being reduced by caffeine really weakly, so it's not really changing a whole lot. Right? Okay, so let's throw in a real reducing agent. Right? So we went ahead, we threw in zinc and HCl. That's a standard, strong reduction, reducing agent. So we did that. We took melling anhydride, we threw in zinc and HCl. That's right. Lo and behold. Well, in solution, Melling Anhydride shows a range of colors. It goes all the way from this nice green, very similar to what we saw with caffeine and Melling Anhydride. It goes through a bunch of other colors, right? Okay, so we did a few experiments there, and then we isolated the green solid, which looked very similar to what we saw with caffeine and Melling Anhydride, right? So we took the solid now, and we ran the NMR spectra. The NMR spectra is identical to the spectra of Melling Anhydride. Exact same. Melling Anhydride, right, if you go to the structure, has only one type of hydrogen, so basically one peak. You look at the solid NMR spectrum, same one peak. Shows up in this. Melling Anhydride is nice and white. This is a green solid. Same NMR spectrum. But you run the melting point, quite different. Melling Anhydride is in the lower 40s. This green solid is more towards the 100. There's a drastic change in melting point. The IR spectrum also is different. Weird, right? For the OChem student. Because you expect IR spectra to match up with NMR spectra, both the investigating structure. But the difference is, right, this is in the solution phase, right? NMR is in the solution phase. Currently, right, our IR spectrometer is solid. So here we took the actual solid and got the spectrum. Here we took the solid and put it in the solvent to get the spectrum, right? So, somewhat better. Okay, right? So here we go, right? So here's Melling Anhydride in red, and pink we have the product. See, so we have some peaks that are missing, some peaks that are, right, obviously present in Melling Anhydride, but are totally absent in the green product. So the IR spectra is definitely different, no doubt. On the other hand, the NMR spectra is the same, different melting point. So, what's the answer? What's a possible answer? Oh, keep looking. Okay, so then we ran mass spectra, right? Okay, let's make sure we're talking about the same thing here. So we ran, okay, mass spectra. That's a peak, you believe me, it's there, right? It comes at, yes, 99. It's the same, right? So this is for pure Melling Anhydride from the stock room, right? We just took it from the stock room, set it for mass spec analysis. Then we took the green solid, sent that away. Same identical peak in the mass spectra, suggesting we have Melling Anhydride. So how is that possible? How come we have Melling Anhydride has the same NMR spectra but different IR and melting points? Well, right? Yes, but then we also ran XRD. And we're currently looking, getting more information from the XRD. The initial observation is they are different, right? The XRD spectra are different, right? Okay, so what we think currently is that maybe what we've made is actually a new polymorph of Melling Anhydride, right? The same compound but having a different crystal structure that's resulting in a different XRD, different melting point, and different solid state IR spectroscopy. That's where, that's the current update on this. Casey is working on this project right now. She's been going to MIT to get some data and examine the spectrum. Right? Okay. The fun thing with polymorphs are, right, widely used in drug companies. Here's just a quick example, right? If you look at tablets, these two are the same compound, except, right, one is a generic tablet and one is a brand name. They're polymorphs, same compound, but one is a polymorph of the other. And this is packaged as a brand name, or the other is a generic name. If you do a quick search on Sci-Fi Scholar, you find all these patents for polymorphs by different drug companies because of the difference in solubility that these polymorphs have, which makes them really useful, right? Okay, yes. All right, so at the end, yes. So what we did do, yes, we went ahead, did some presenting of data. All right, here is Tyler, Curtis. Look at the transformation. These are the same four guys that I showed in the first. That's what happens, see? All right, and some of these faces you guys will recognize. Holly and wow. Nice. We got to do some presentations at ACS conferences. Yes, Sam. Yes, Mikhail. Right. We got a few papers in. See? Nice. Very nice. What about the candles? Let's get over the candles. Right. Well, basically, right, we now have an improved understanding of the PCO chemistry bond, which is really not found in literature. We got some data on that. We have some new information on how BRCO bonds work with regard to phosphine, so a little light on that. Huh? And some caffeine and Melling Anhydride chemistry, right, that we're currently doing. Very nice, very nice. Burning question? That's all the chicken biryani. Oh. Okay, well, there's no time for that, so we'll just let that be. All right, so usually you ask me the questions. This time I'm asking you the questions. See? Nothing tastes better than A. Chicken? Pizza? No. Chicken? Burgers? Chicken? Soup? All right. So let me want to thank all the students, right, who basically done the work, and so these are a list of students that got to do this work, and surprised the number of students that had the opportunity to work with. It was really fun working with undergraduate students. So these are some of the ones who have left, right? And these are some of the ones who are currently here who have worked with me. I want to thank the biology department and chemistry, the facilities, and for you guys for listening to this. Thank you very much. Any questions can be asked?
So we have time for a few questions.
Yes.
Yes,
I
Nate.
distinctly remember taking an NMR for you last week. I think you're missing. No, I'm just kidding. Back in your bromine reactions, you might want to go back to one. I was just curious as to when you were getting the brominated phenylphosphine, what the side, like what the minor product was to that.
Right, so you're asking about these reactions, right?
Yeah.
What the other product was.
Yeah.
Right, so we couldn't trace the product in solution.
Okay. I was just curious, do you guys look at all into, maybe this was 20 minutes ago, I had a question. Like using excess phenylphosphine, or, just what would happen after all of the bromine in the solution had been used up to make that, and then adding more phenylphosphine to it? Or?
So you're asking what would happen. Okay, so once we actually isolate this one, then to the remaining solution add more phenylphosphine?
Yeah, or just, using phenylphosphine in excess as opposed to 1-to-1 ratio, or?
No, we did ratios, we've done ratios, but we haven't, we did not do what you mentioned before. That is isolate the dibromide, and to what is left in solution add more phenylphosphine. We didn't do that. Yeah.
Okay. I was just curious what would happen, not necessarily isolating your product, because then, you could have something stable left in the solution, obviously, but just what would happen after all the bromine had reacted with your phenylphosphine as to then push it further to forcing the phosphine to react with
CO, right? Yeah, good question, yeah. We haven't done that. We didn't. I know, we've done different ratios and we pretty much get this. As long as there's BR there, it seems like it's going to go for it. Right? And the only way you have BR is if you have the acyl bromide. And as long as you have BR and acyl bromide, it's going to, no matter how much phenylphosphine we have, all that's going to react to form the dibromide. So any remaining phenylphosphine is just going to be phenylphosphine.
Okay.
So what do you think? Yeah.
Any other questions?
I have a question. So did we ever look at the differences between the methods, the gel method and the other method that you guys use to get these spectras? Because it appears that the difference between the two is just one is more pronounced. You still have two peaks,
Yes.
but one is kind of very resolved high resolution, the Jobs method.
The Jobs, yes.
Are there any differences in these two methods that could explain why one looks like that rather than the other? Or do we know? Do you guys ever looked at that?
So the Jobs, so that is the solution, okay, that's the solution phase. Jobs method. Like with these two peaks, right?
Yeah. So if I look at this, I can see there's two peaks in the bottom two. In the bottom one.
Oh, this one.
Yeah.
Okay, so that's, yeah, so you're trying to relate this with this.
Right. So the only thing is they're more resolved in the Jobs method. Than
Right.
Yeah.
Yeah, yeah, so it looks like it goes along
Yeah.
with this. You know, the problem is this is, you know, this keeps going up. So really not sure.
Right.
You know, this is suggesting, to me, this is suggesting we're having more than two complexes. This seems to suggest two complexes, but this data is suggesting we have more.
Okay.
Maybe it's just too weak,
Yeah.
maybe not different enough to show up in Jones method,
Yeah,
could
yeah,
be.
yeah.
Right?
Okay.
Could be.
Well,
Any more questions? I have one. Why, when you do these chemical reaction figures and so forth, why do you do a hexagonal instead of a circle? Okay, let's thank our students.
Maybe next time.
he got you on that one, didn't he?